Okay, it's a pleasure to introduce Jianzhu. He's a PhD student in Jianzhu Ma's lab at TTI Chicago, and their lab is known for some of the foremost protein threading algorithms, and today we're going to hear about a really nice approach as to how to improve protein threading. And this, I believe, has performed really well in the CAS competition last summer.
Hello everyone. Today I'm going to present my work on conditional neural fields model for protein threading. So my name is Jianzhu Ma. I'm from Toyota Technology Institute at Chicago. This is a joint work with Jianzhu Ma and my advisor Jianzhu. So in this work, we try to focus on the problem of protein structure prediction problem. So the reason why we want to know the protein structure is because protein is able to perform specific functions because they can fold into specific 3D conformation. And many diseases are caused by misfolding the protein structure. So in order to better understand the protein function, it's quite important to know a protein structure. So here, the task is, given amino acid sequence, we want to know its 3D structure. There's usually two ways to do that. The first is using experimental techniques. It's very accurate, but it's time-consuming, it's very expensive. Another way is using the computational methods. It's high throughput, cheap, but right now it's not very accurate. So in this talk, we're going to use computational methods, template-based modeling to predict the protein structure. In contrast to the complete template-free modeling, the template-based modeling used already solved the structure to solve the protein structure prediction problem. The template-based method can be successful mainly because although there's a lot of protein structures in the PDB, the known unique fold are very limited. And based on statistics, that numbers grows quite slowly each year. The methodology of the template-based method is also quite simple. So given a protein structure, given a protein sequences, you basically do the alignment against all the templates in the database, and you just run some algorithm to find the best one, and you can get the structure. And following that procedure, we can know that the final protein model quality depends on two things. First is if we can correctly identify the correct template. And the second is, given us the template, if we can make an accurate alignment. And in another hand, if we can correctly identify the template, still depends on if we can make accurate alignment. So you can see the bottleneck of the whole template-based method is really lies in the if we can make accurate alignment. So talking about the alignment problem, alignment is hard. In sequence and template, their sequence identity is low, usually lower than 30%. And you may wonder that, do we have to do the alignment when sequence identity is so low when we're using template method? And the answer is yes. According to the statistics in the mode base, nearly 76% of the models are built from sequence and templates with lower sequence identity. So in other words, if we cannot make an accurate alignment on those regions, we cannot make a very good model. So in order to make an accurate alignment, what kind of information we can use? First, we can use sequence information. It's easy to know that for if two proteins, their sequence is similar, it implies they have similar structures. So many methods based on the sequence-based method like BLAST and FASTA, and they usually work for close homologous proteins, which means they have high sequence identity. Sorry, this doesn't work. And the second is, even though in some cases the protein sequence is not similar, they may still have similar profiles. And the similarity of the profiles also imply they have similar structures. A profile definition is, according to Wiki, it's a matrix that represents multiple sequence alignment of the similar proteins. So basically, for each positions, we have 20-dimensional vectors represent the mutate frequency with this residue against the other 20 residues. So we usually use NEFF to quality the profile, to measure the profile quality. So the NEFF can be computed as the average entropy of the multi-sequence alignment. Usually if the NEFF is high, it means it contains more profile information. If it's low, it contains low profile quality, profile information. And many well-known profile-based methods includes HPRADE and HBR. Now the challenge is, so the similar structures may not imply they have similar sequence or similar profiles. In order to solve this problem, people add structural information into the sequence and the profile-based methods. And that is called protein threading. So many well-known protein threading tools including SP3 and the Raptor and the Moomster and the Bootstrapper. So now we have three kinds of information. We want to know when will each kind of information help in the protein threading. So look at this region. Look at this example. Now we have two proteins and we want to do alignment. There is some region with very high sequence similarity, and there is some other region with very high profile similarity. There's also some regions the sequence and the profile are not quite similar, however, they have similar structures. So now the question is, it's not a 0-1 problem. We use either of the one of the information. We want to use all of them. So for given proteins and for each position, we need to quantify the amount of evolution information and the structure information we use. And how to do that? So the way we solve the problem is we use a machine learning method called conditional neural field to solve this problem. The conditional neural field is composed of conditional random field and the neural network. So in this problem, we use the conditional random field to model the protein alignment state transitions and use the neural network to model the complex relationship between different features. After setting down the models, we train the model using a quality-sensitive training method. So at last, we just general alignment using traditional weighted algorithm. So first, I will introduce you how to model protein alignment using CNF model. So first, the given alignment, we can treat it as a string, a sequence of different states. It's quite easy. So if these two residues are matched together, we call it match state. If there's a gap on the sequence, we call it insertion and sequence. Then when there is a gap on template, we call it insertion and template. And this alignment can be formalized as a string of different states. And that finding an alignment is corresponding to, in this graph, with template and sequence, finding a unique path from this corner to that corner. So given the alignment, we can compute this probability, right? So the probability of alignment given the template sequence is proportional to exponential form a summation of energy functions and normalized by some normalization factor to make sure that the probability of all the alignments in the alignment space sum equals to 1. And here, the energy function is the neural network that estimating the log likelihood of the state transitions. If you look at this in this graph, suppose you're standing here in the mesh state, you want to determine what's the next state you're going to go. You want to go do an insert in the template or insert as a sequence or keep match. So the likelihood of different state transitions is the neural network. So that neural network takes the local features of template and sequence, and then transforms all the features using a lot of hidden neurals and output a real value to estimate the log likelihood, to estimate if we can go this way, or that way. So suppose we have a model, how can we train this model? So here we develop a new training method. Because we use a reference alignment, we use structural alignment as the reference alignment, we know that there's, on this structural alignment, there's different regions. Suppose this is a reference alignment, even though they are aligned together, however, if you look at the superposition of the two proteins, there are some regions which is quite conserved. There are some regions, well, it's not. They're not superposed very well. They have very large MSD here. So we want to discrete these two regions so that our model will focus on this conserved region and will not misalign those conserved regions. The way we do that is, instead of maximizing the log likelihood, we're maximizing a summation of weighted marginal probability. So on the marginal probability, we put a weight here. The weight is the local TM score, which can be recognized as when the local MSD is large and this weight is small, and the local MSD is small, this weight is large. So our model, we can say that if the line positions, if their local MSD is quite large, this weight will be small. So that maximizing that function will make our model focus more on the conserved region instead of treat each line position equally. So if you notice, changing the log likelihood maximization to the quantity-sensitive training will actually change the log likelihood to the marginal probability. That will increase a lot of computation complexity. So we developed an algorithm called double forward algorithm to do the quantity-sensitive training so that our computation complexity is still the same as the training the log likelihood. So in this model, we use a lot of features we mentioned before. For sequence information, we use amino acid substitution matrix like Blossom and Garnet. For profile information, we use query sequence and profile templates profile. We call sequence profile information and profile information. For structure information, besides using traditional 3 class of segment structure, we also use 8 class segment structure, and we also use 3 class of solid accessibility similarity score, and we also developed a score called the environment fit score. And besides using all these kinds of information, we also use what we call a neighborhood score. The intuition is suppose two residues, their neighbors are very similar. It's highly similar. They two can be aligned together. So using these all features, we put these features as input of the neural network, and this function is our total scoring function. So the training data set and the validation data set all come from what we call PB25, download from database of pieces, which is a work of one and a downbreak. And each of the proteins in this training set and the validation set share a sequence identity smaller than 25%. And for training data set, the proteins covers most of the scope folds, and there's no redundancy between the validation set and the training set. So to generate reference alignment, we use our own structure alignment tool, deep align. So if you went to 3D6, and we introduce our new method there. So finally, we evaluate our performance using 4 benchmarks. First, we construct our own in-course benchmark with a very large data set. Contains 2,600 protein pairs. It contains all kinds of protein classes, including all alpha proteins, or beta proteins, and alpha beta proteins. And the NEIFF, which measures the profile quality, is also uniformly distributed. And we have different lengths of proteins also widely distributed, and the TM score is between 0.5 to 0.7. And next, we use the Muster benchmark, which is a work by John's group. It's composed of 100 Proxon pairs and 190 pairs selected by John's group. And each pair have TM score larger than 0.5. And we can see that even structural alignment can get only 0.5 TM score. So these two benchmarks is really quite hard. And there's two relatively easy benchmarks called SLN benchmark, which contains 200 pairs, and Proxon benchmark contains about 127 protein pairs. So first, we evaluate our performance using reference-dependent alignment accuracy. The reference-dependent alignment accuracy is computed as we just compute the correct aligned positions with respect to different kind of reference alignment. We use different reference alignments because our method is trained using deep align, so we certainly don't want our method to have some bias on particular reference alignment, so we evaluate our performance using all kinds of structure alignment tools. As you can see, on these two very hard benchmark, our performance is much better than the second best method. And yes, it's better. And this BR represents the benchmark's own reference alignment. Now we can see on this relative easy S-aligned benchmark, our performance is also the best. However, it's not better than the second that much, which is makes sense because this benchmark is relatively easy. And on the most easiest benchmark, props up, our method is is still the best, but not that the performance is not that high. Besides using reference-dependent alignment accuracy, we also compare our reference-independent alignment accuracy. So the reason why we use reference-independent accuracy is because you cannot just compare the correct alignment positions, because in the alignment space, there's a lot of alignments share the same sequence, share the same correct alignment position. However, if you make a model, these alignments will be performed very, very different. So we use this alignment reference independent alignments to compare our models. So it is computed as first we choose one of the proteins as a template, and we recover the model using the alignment, and compare the model with the native structures. And the model similarity is measured by TM score, which is the real value from 0 to 1. And this is the higher the better. So we just, for each benchmark, we just sum all the TM score together to see their performance. As you can see, our in-house benchmark and the Mooster, which is the hardest two benchmarks, our performance is significantly better than the other two. The second best method. And one of the good things of our in-house benchmark is we can easily divide it into different groups according to different criteria. So here we first divided our in-house benchmark according to NEFF, which measures the profile quality. So when two proteins NEFF is both larger than 9, we just put into this bin and so on. As you can see that when the NEFF is large, which means the profile quality is very good. All of the method actually works all very well, but our method still is the best. When the NEFF force equals to 1 to 2, our method is significantly better than the other two methods. So next, we divide our in-house benchmark according to the protein classes, and we can see on the all beta protein classes and all alpha proteins, we improve the performance a lot, which is very hard to improve because on those two classes, using traditional 3-class second structure really doesn't help us much because they're all alpha, all protein. So in this way, because we use more information like 8-class second structure and the stored accessibility and the environment fit score, so we can improve the performance on those two classes of proteins. And this picture just shows that our method still works with respect to different protein lengths. And at last, we evaluate our performance using strategy, which means we compared our method with our method to find the best template in the database. We compare the best template and build model. We compare that model's quality to see who gets the better model. So the data set is constructed by using 1,000 protein pairs downloaded from PDB20 file database, and we're predicting structures of a specific protein. The protein itself is of course removed. And suppose because we have a lot of templates, how do you determine which is the best? So we train a neural network using CNF alignments, and output a real value score. That score, we just pick the best scores template. And we compare our method with HHPRE. The x-axis means the TM score difference. So if, for example, in this bin, it means that there is 500 models which we have about 0.01 TM score than the HHPRE, which this group, this purple is our method. And you can see that we have at least 200 models in these 1,000 proteins, which we have about 0.1 TM score compared to HHPRE. So in summary, in order to solve the protein threading problem, it's quite important to make an accurate alignment. And in order to make an accurate alignment, it's important to quantify the amount of evolution information and structure information. And to solve this problem, we build a CNF model. And the CNF model is a combination of a CRF model and neural networks. And we developed a new quantitative-sensitive training method to train the model. And the last, we use different features as sequence information, sequence profile information as features. And finally, we evaluate our performance on several different benchmarks. And just many acknowledgements. The first is work supported by Nash Ground and NSF Ground. And we also thank the Chicago Beagle team, Tara Green, and the Canadian Sharp Knight to carefully share their computation resources. And this presentation of this work was made possible by a travel fellowship awarded by ISCB with grant funds often from the DOE Department of Energy Office of Science. Well, thank you for your attention. Thank you.
Any questions?
Well, I have a few questions actually. First one, how computationally intensive is the method? So how long does it take to thread, let's say, one protein onto your whole PDB template set?
So that really depends on the protein length.
Let's say 200 amino acids.
200 amino acids will be very quick because what I show you is the training the method. You train your model just using once, and then when you decode, you just use the traditional weight-B algorithm, right? So it's very fast. It's not as fast as any method we get.
Okay. Then the next question is, do you plan to make the method available for the general public?
Yes, yeah, of course. We are going to release our program and put it on our server, just after class.
Okay, well, we've waited quite a while for RaptorX to be available. And
I also want to share, my code.
And well, the last thing, I couldn't really help but notice that you have dashes in your benchmarks, mostly in comparison to master. Is there any reason for that? Why there's no data? Why the tables are not full?
Yeah, it's like first the Mooster benchmark is used for Mooster streaming.
No, but you had actually in one of the tables you had results for master, like master benchmark and master as a method, but you didn't have the results for all the other benchmark sets.
Yes, but I'm not sure.
Like show the table.
You can show the slides.
Yeah. That would be much easier.
Here, yes.
For example, the table that we just passed by.
You mean the previous one?
No,
No.
okay. The other direction.
There.
Oh.
There. Yeah.
Oh, there. Yeah. So you see, you don't have the results for mastering for your in-house dataset S-align ProSub. Is there a reason for it?
Yes, suppose there's, of course, I didn't compare all of the other methods because firstly, we certainly don't get reach of their program, and we cannot just put all of the 3,600 protein pairs on their server, so I can...
No, but you said that those are actually so you didn't compare your, but master is available, right? As a program, you could download it and run it.
So each program is different file formats. like for the target and the template, must use a different format. Then it's really challenging for us to get the file content.
No one can hear you.
Well, it depends on Okay, I heard your answer.
Yeah, so my answer is because of the different file formats used by master. So, for example, even if you can download the binary code from master, but you still have to generate the template files and template file, which can be used by master. So this is very challenging.
Well, okay. Well, master comes with the template library, but I understand that it's computation intensive. But you compared master to all the other in other benchmarks, so.
Your other benchmark I just downloaded from copy number from their papers. They put their numbers on the papers.
Yeah, I understand that. Okay, thank you.
Okay, I just want to let everyone know before you clear out, there is another talk that was slotted